So a random variable x is distributed normally with a mean of 20 and a standard deviation of 4. On the following diagram, shade the region represent p is less than or equal to 25. So the first thing you can do is you can draw your mean in the middle, go 3 standard deviations above and 3 standard deviations below. In this case, I only drew the 3 going above. Find out where 25 is, and then shade the area less than that. Mental math, quick estimate. What do you think that area is? How could you use the 68, 95, 99.7 rule to estimate that area? Would you agree that up to there would be 50%? Now, the 68, 95, 99.7 rule, which is for estimating, says that if you go 1 standard deviation above and below, that's 68%. So since it's symmetrical, up to 24 would be approximately another 34%. And we have a little bit more than that. Now you would be guessing how much that extra 1 would be. Right now we're at 84%, so we might estimate this to be approximately 90%. As far as the area under the curve would be then, well, I'm going to put a 3 sig figs, 901. No, I have no idea. But as far as an area, the area under the curve is a decimal. The whole area adds up to 1, so we would estimate that. And then it says write down, correct to 2 decimal places. Oh, so close. So this is an exam question. All year, what do you get drilled into you for rounding? 3 sig figs, right? What do they do on this exam question? 2 sig figs, just to see if you read to the end of the question. Nice. Let probability x less than or equal to c equal 0.7. So now we're imagining, if we draw a little, I love drawing the little curves. There's c, that area is 0.7. If we're given the percentage and we want to find a score, that's where we use the inverse norm. And so we get 22.1%. So you've got these, with normal distributions, you've got the 2 main functions, normal CDF and inverse norm. Normal CDF will always find the area under the curve or the percentage. And inverse norm you use when you know the area under the curve and you want to find the score. The value that goes in here for inverse norm is always from the left. So if they asked you, find the score that represents the top 30%, the score that separates the top 30%, you would still put in 0.7, because for the top 30% from the left would be 70%. All right. The weight of newborn babies in Australia are normally distributed with a mean of 3.41 kilograms and a standard deviation of 0.57 kilograms. Right? So we could compare this to find out, are babies in Australia heavier than babies in Canada? Right? So Maybe, you know, one day in your life you're expecting your first child and you're like, oh, I don't want a very big child because I don't want to go through a hard labor, so maybe I'll fly to Australia. Would that? No, that doesn't actually affect it. But there are people who think that way. They find out, oh, right? Different statistics are out there. Well, I'll show you some statistics. There is a math Google site. It's called Wolfram Alpha, and it is like the Google of math. You want to find anything math related, you go to that website instead of Google, and it tells you all the math about it. So I'm going to show you some statistics from there afterwards. Okay, a newborn baby has a low birth weight. Find the probability the baby weighs at least 2.15 kilograms. Or sorry, A. Given that 5.3% of newborn babies have a low birth weight, find W. So we're given the percentage. We want to find a score. That's going to be an inverse norm. If you wanted to draw a quick picture of your normal distribution and shade a part, there's your 5.3%. So inverse norm from the left, 0.053, mean and standard deviation goes in there. You would find out that that value is 2.49 kilograms. Any baby born under that would be considered to have a low birth weight. A newborn baby has a low birth weight. Find the probability that the baby weighs at least 2.15 kilograms. Okay. What kind of question is this? I mean, we're in normal distributions, but it's a conditional probability question. So we're starting this, the examples that we're doing here, starting to say, what happens even if we try to connect separated things in this unit? So if we set up our formula, right, or set up our, here's our formula. We want to find the probability. It's greater than or equal to 2.15, given that the baby was lower than normal. Okay? The given is always what you write here, and it's always the probability on the bottom. So sometimes with probability, I think we find that just writing out the notation sometimes, like, I put this up, and it's sort of like, whoa, what does this all mean? It takes some time just to think about what do each of these things mean. So we're finding the probability that x is greater than or equal to 2.15, given that x is less than w, meaning that it has a low birth weight. At the top of your conditional probability, it says you would do the probability of this and this. So if I want bigger than 2.15 and less than 2.49, or less than, so that it is a low birth weight, I can write that as x has to be between 2.15 and w. Divided by what's the probability of a child being low birth weight. So if we put those values in to our calculator, so normal CDF of 2.15 to 2.49 will give us the chances of that baby being between 2.15 and 2.49, divided by the probability it is of low birth weight, gives us a 75% or 74.5% chance of this happening. Masses of watermelons grown on a farm are normally distributed with a mean of 10 kilograms. So as soon as you see that in the question that they're normally distributed, you know that you've got normal CDF and inverse norm and can use all of those. Watermelons are classified as small, medium, or large. Ever seen those rectangular prism watermelons? There's like special places you pay extra for them. They actually come in watermelons that are perfectly cubes. They were grown that way so that they would stack better in superstores and stuff like that. And you pay extra for them. So they grow the watermelon in a rectangular box so that the watermelon is forced to grow into that shape, and then they can, I guess, make it bigger as it goes. Like, I don't know if it's worthwhile, but it's fun. Makes me think, what other shapes could you make? Like, could you make a watermelon in the shape of an elephant? So you have an elephant watermelon. I don't know. Okay. A watermelon is small if its mass is less than 4 kilograms. 5% of watermelons are classed as small. So at that point, inverse norm or normal CDF are you thinking of? Inverse norm. We need to find the standard deviation of the masses of watermelons. And the following table shows the percentages of small, medium, and large watermelons grown on the farm. Okay, so let's answer part A. We know that the probability that it is small is 5%, but we don't know, and what I've done here is I've put on the z-score and looked at your z-score formula because we don't know the standard deviation. So if we draw a diagram of what we do know, and I'm going to use the letter S here right now, that that is 5%. And we know that the mean is 10, but we don't know the standard deviation. And so we're going to have a tough time finding S from this directly. However, if we think of this as a standard normal curve with a mean of 0 and standard deviations of 1, we could find the z-score for S. So if I go to inverse norm of 0.05, it's not wrong if you put in 0 and 1. But your calculator, if you just write inverse norm of 0.05, it will assume the mean is 0 and the standard deviation is 1. Trying to remember, when you open up inverse norm, does it start with 0 and 1? I think it does. We'll check it. Yeah, so we go to distributions, you go to number 3, inverse norm. It automatically puts 0 and 1 in there for you. Oh, look at this. We have all the right numbers. And so we get that it is equal to negative 1.644. You could take your z-score formula, 4 minus 10 over sigma, and we could now calculate that our standard deviation is 3.65 kilograms. So going up to read and continue with the question, part B says, find the value of W. A watermelon is large if its mass is greater than W. Well, we've got the percentage here. We could do this exactly the same way that we did A. But in this case, we've already got our standard deviation. So we can put the mean and the standard deviation in. Why do I put 0.62? For a large watermelon. Where does that number come from? If we look at the values there, none of them are 0.62. Large is to the right. Right, so if we draw a little picture of this, large is right here. I'm going to use L. This is 38%. An inverse norm always calculates a score from the left. And so if this is 38%, this open spot here is 62%. And so inverse norm comes from the left. We would use 0.62. And that is a big watermelon, 11 kilograms. Okay? Part C. All the medium and large watermelons are delivered to a grocer. A grocer selects a watermelon at random from this delivery. Find the probability it's medium. So just like the question before, what kind of question is this? It's conditional probability. Okay? In fact, this is conditional probability I think you could almost do mental math for. What percentage of watermelons are delivered to the grocery store? 95%, all except for the small ones. And how many of those 95% are the medium ones? 57%. So find the probability it's medium is just going to be 57 out of 95. If you think of having 100 watermelons, 95 are at the grocery store. Of those 95, 57 of them are medium. Now we can do this with a formula as well. We can set it up and say, what's the probability of a medium one given that it was delivered? And you can look at your overall percentages, 57 out of 95, which is 0.60. And finally, for part D, okay, a grocer sells all the medium watermelons for $1.75 each, and the large watermelons for $3 each. His costs on this delivery are $300, and his total profit is $150. Find the number of watermelons in the delivery. So you get into your exam. This is an exam question. And part D is designed for you to say, oh, we did one just like this in class. No. Part D is designed to be like, I've never seen a question like this in class. I'm going to have to think. Would you agree? Right? It's not like after this, can I have Mr. JR, can you give me 15 more watermelon questions so that I'm ready for the exam? Well, no. We have to be ready for any type of question. And you will find in a question like these that are longer, like this one was out of what? 5, 10, 14 marks. Okay? A 14-mark question. They will be designed this way Part A, Part B, Part C were fairly straightforward, and I would say are connected to the things that we've done so far in this unit. And then Part D is designed for you to think. So let's say X is the number of watermelons in the delivery. We figured out in Part C that 60% of them are medium and 40% of them are large. Since you sell the medium ones at $1.75 and the large ones at $3, why do I have it equal to 450? 300 plus 150. And why would it be 300 plus 150? Right, because it's our profit. Our profit plus the costs would have to equal the revenue that you brought in, because your profit in the end is how much money you brought in minus your costs. So you would have to bring in $450 in the end. Now that we've set this up, this is the hard part, was interpreting that question and coming up with this equation. Once you have this equation, the math itself isn't too bad. Solve for X, and you had to have 200 watermelons. How many marks was this one? 5 marks. Okay? It took us 3 lines once we thought of it. Okay? Probably would have allotted 3 marks for the equation. 1 mark for figuring out the 450 was important. 1 mark for using the proper values of 60% and 40%. 1 mark for simplifying your equation, and 1 mark for your final answer. Yes?
If